All right, in this video, we're going to take a look at the worksheets that you picked up in class. I'll also post these on Google Classroom if you need to download them. So have this in front of you as we go and work through it with me. Don't just copy down answers as you go. So we're looking at reaction mechanisms and a quick review of some potential energy diagrams. The big idea here, though, is reaction mechanisms. You remember that a reaction mechanism is the sequence of steps or collisions that occurs in any chemical reaction. Most reactions do not happen in just one collision or one step. They happen through a series of steps. And so that's the reactions mechanism. In this first question, you can pause the video and just read over the introductory paragraph. So we're looking at the decomposition of hydrogen peroxide, H2O2. It decomposes to make water and oxygen gas. We're told that this reaction is very slow at room temperature, but there's enzymes, catalysts, which will speed it up. In the presence of one catalyst, HBr, hydrobromic acid, there's a two-step reaction mechanism that will take place. In the first step, the HBr catalyst reacts with the hydrogen peroxide molecules. They collide. Notice there's three particles there colliding, two HBrs and one H2O2. So we would say that that is a termolecular step. Okay, two particles colliding like that. In the second step, the bromine, which was produced in the first step, becomes a reactant in the second step, and it collides with another hydrogen peroxide molecule, and they form HBr again. Hey, that's the same catalyst that we began with, right? And oxygen. In the second step, there are two particles colliding, so that second step is referred to as a bimolecular step. If there was only one particle and it was, say, decomposing in a step, we would say that that's a unimolecular step. So unimolecular, one particle decomposes, bimolecular, two particles collide, termolecular, three particles collide. And you recall from collision theory that the probability of there being any more than a termolecular step, any more than three particles colliding at once, all with the right geometry and all with the right energy, that is just such a low probability that you don't see it happening. So termolecular is the highest molecularity for any step that you're likely to see. So now part A says write the balanced equation for the overall process. So what you want to do when you're writing the balanced equation is cancel out anything that appears on both sides of the reaction mechanism. So for example, we have two HBRs on the left, and then in the next step, two HBRs on the right. So cancel those out. There's a bromine on the right in step 1. There's a bromine on the left in step 2. There you go. So whatever's left is the overall reaction. So in this case, there'd be two H2O2 molecules, the one from the first step and the one from the second step, and they are producing two water molecules and one oxygen molecule. And you'll notice that that is the same as the original balanced equation at the top of the page. Now, what is an intermediate? You remember that intermediates are products of one step, but then they're reactants in a later step of the reaction mechanism. Not necessarily the very next step, but later in the mechanism, they're a reactant. In a two-step mechanism, there'll be products of step 1, and there'll be reactants in step 2. So in the mechanism we see up above, bromine was produced in step 1, bromine was then used up as a reactant in step 2, so bromine is the intermediate product. Catalysts are sort of the opposite. A catalyst is added to the reaction early in the reaction mechanism. It's a reactant at first, and then later it gets produced again. So in a later step, it's a product. That way, the catalyst doesn't get used up, which is part of the definition of a catalyst. It speeds up the reaction, but does not get used up. So in the mechanism above, The HBr was a reactant in the first step, and it was produced again in the second step. So the HBr was the catalyst. The catalyst changes the reaction's mechanism, and in this new mechanism, this is really important to understand, the new mechanism is faster because it has a lower activation energy than the uncatalyzed reaction. Now, catalysts can be homogeneous or they can be heterogeneous. They're considered homogeneous if they're the same phase as the other reactants. Remember, the prefix homo means the same. In the original reaction, the hydrogen peroxide was aqueous, and our catalyst is aqueous. So because the catalyst and the hydrogen peroxide were both aqueous, this is going to be a homogeneous catalyst because they're the same phase. If you put a solid catalyst in with an aqueous reactant, then now because they're different phases, that catalyst would be considered a heterogeneous catalyst. Heterogeneous catalysts are very common when the reactants are gaseous. If you have gaseous reactants, it's common to see a solid catalyst, and so those catalysts are heterogeneous. Part E, how can a small amount of catalyst decompose large numbers of particles, of hydrogen peroxide particles? Pause the video and see if you can answer that yourself. So looking at the reaction mechanism, because the catalyst is produced again in step 2, the catalyst can go on in another collision to decompose more hydrogen peroxide. So because it's produced again in a later step, it can act again as a catalyst in another set of collisions. Now that might lead you to think that a single catalyst particle could end up over long periods of time decomposing all of the reactants, right? But that doesn't usually happen, one, just because of the random nature of the collisions and the length of time that would be required, but also because there are other collisions happening, right? Although we're focusing on this particular set of collisions and this mechanism, remember these particles are in water and they're colliding with other molecules. So in some reactions, the catalyst might actually get used up. Not in this mechanism, but in some other reaction. So if that happens, the catalyst will be gone and it will not end up decomposing everything. Part F, pause the video and write a definition. So you should have said something to the effect of that the reaction mechanism is the series of steps or the series of collisions that describes an overall chemical reaction. Something like that. Question 2, the next page, we're shown a potential energy diagram for the uncatalyzed decomposition of hydrogen peroxide. If I just trace this with my highlighter, the uncatalyzed potential energy diagram is this one. Okay, so notice that it has a pretty large activation energy. The activation energy is the difference in energy from the original reactants to the activated complex, or the transition state, which is at the top of that hill on this energy diagram. So that was the uncatalyzed reaction, and there's only one hill. So in the uncatalyzed reaction, it would have been a single-step process with a large activation energy and therefore likely to be very slow. Let me erase what I just drew there. In the catalyzed reaction, remember in the previous page, it followed a two-step mechanism. And if you look back, okay, the two steps, the HBr became bromine when it reacted with the hydrogen peroxide, and then in the second step, we produced HBr and oxygen again. So if you compare that to here, we can see, I'll trace this now with my pen. So the original reaction now follows this two-step process, and that is the catalyzed process. So what was the effect of the catalyst on the activation energy? Pause the video and answer that. So in this new mechanism, the first step's activation energy is there, and the second step's activation energy is here. So notice either step, the activation energy in the new mechanism is lower than the activation energy in the original mechanism, which is why it was faster. So the activation energy with the catalyst is lower than the activation energy in the uncatalyzed reaction. Part B, see if you can answer that. So this assumes you remember potential energy diagrams. The delta H, the heat of reaction, is the difference in potential energy between the starting reactants and the overall final products for the overall reaction, right? That's what we're looking at. So notice that the catalyst didn't change the potential energy of the original reactants, and it doesn't change the potential energy of the final products. So therefore the delta H overall was unaffected. Okay? Part C, pause the video and try to answer that. So of the two steps, which one was the rate determining step? Well, the rate determining step is the slowest step of the mechanism. You should remind yourself of that. And therefore, it's the step that has the largest activation energy. So looking at the two activation energies that I drew, the one that's the largest is the second one. Not because it reaches the highest point, but because the height of that second hill is taller than the height of the first hill in the two-step mechanism. So step 2 was the rate determining step. If you went back to the original mechanism, you could now add that step 2 was the slow step and step 1 was a fast step. When you say that, you don't mean literally slow and fast, you simply mean relatively step 2 is slower than step 1. So step 2 has the higher activation energy and is the rate determining step. Question 3. Pause the video and see if you can do this yourself. So we're talking about ozone and its destruction high up in the atmosphere by CFCs, chlorofluorocarbons. And one such, the chlorofluorocarbons are a whole category of molecules, but they have chlorine atoms attached to carbon chains. When they get struck by ultraviolet light, they release chlorine radicals, basically a chlorine atom that is missing one electron. So it's highly, highly reactive. In the two-step mechanism, we cancel out the things that appear on both sides of the reaction, just like we did earlier. So the hypochlorite gas, or I guess that's not an ion, the chlorine monoxide gas that is produced is used up in step 2. So we'll cancel it out. Also, the chlorine atom, that radical, was used up as a reactant in step 1, but it's produced in step 2, so we can cancel it out also. Cancel whatever appears on opposite sides of the equation. Now, whatever we didn't cancel is the overall reaction. So we have 2 molecules of ozone. I'll leave out the phases to make it simpler. That's going to produce 3 molecules of oxygen gas. Notice that your overall reaction does have to be balanced. If it's not balanced, you've missed something or you just copied something down incorrectly. So now identify the catalyst. The catalyst is a reactant at the beginning and then a product later on. So it's a reactant in step 1 and it's a product in step 2. It was canceled out. So Cl gas is a catalyst. Is it homogeneous or is it heterogeneous? Well, the other reactants were also gas, right? The ozone molecules were gaseous. So that means it was a homogeneous catalyst. When it's the same phase as the other reactant, it's homogeneous. The intermediates are sort of the opposites of catalyst because they're produced in an early step and they're used up in a later step. So they're a product at the beginning and they're a reactant later on. When I say they're sort of the opposite, that's all I mean. Okay, they're not literally the opposites. They don't slow down reactions. Intermediates are just in a mechanism in the opposite orientation. So produced in an early step and used up in a later step. So in this reaction, the ClO gas. Notice that catalysts and intermediates will always be canceled out when you write the overall reaction. The catalysts and the intermediates will never appear in the overall reaction. So they have to be canceled out in the mechanism. So chlorine is normally a diatomic element. It's one of our Hofbrinkel elements that have subscripts with 2. Here we have chlorine that's a radical. It's just an atom of chlorine, and I mentioned it's missing 1 electron. Write a balanced equation for a reaction collision that could remove the chlorine radical. Well, it's very simple. 2 chlorine atoms that are in the atmosphere could collide, and if they collide, they'll form chlorine gas, Cl2. Now, chlorine atoms, those radicals, were catalysts in the destruction of ozone. Chlorine gas, Cl2, is not a catalyst in the destruction of ozone. So when the chlorine atoms collide like that, they are being removed from the atmosphere in terms of destruction of ozone. So the catalyst, that would be called technically a termination reaction or a termination step, because the catalyst is being removed or terminated. Right, I'm not gonna do all of these with you, but I'll do the first one with you, and then I'll leave you to finish off question 4 on your own. So we're going to simply write the overall reaction, any catalysts or intermediates, if they exist, in the reaction mechanisms. So the first one, let's do this together. The overall reaction, well, let's cancel things out. So the 2 NOs that are produced in step 1, they get used up in step 2 as reactants. That means that the NO gas is an intermediate. It's produced in an early step, used up in a later step. Is there a catalyst in here? Well, I'm looking for something that's a reactant in step 1 and a product in step 2. I don't see anything, so there is no catalyst in this mechanism. Then the overall reaction, whatever I did not cancel, would be nitrogen gas reacts with 2 oxygen molecules to produce 2 NO2 molecules. Just a quick review of what we said earlier. The first step with 2 particles colliding, you'd refer to that as a bimolecular step. The second step has 3 particles colliding, 2 NOs and 1 O2, so the second step is termolecular. If there was just 1 particle as a reactant, you'd refer to that as a unimolecular step. All right, so you can finish the rest of this off. I'm not sure, but it's been a year since I've used this worksheet. There might be an issue with this last one, so if you get to it and there's something strange there, just delete that last question. Question 5 shows us a potential energy diagram, and we're going to answer the questions down below. See if you can pause the video and try this yourself. So part A, how many collisions? Well, to see the collisions, you just look at the number of hills. So there's 1, there's 2, there's 3, there's 4. So there were 4 steps in the mechanism. Which step is fastest? Well, the fastest step has the lowest activation energy. The first step's activation energy would be here. Let's call that EA1. It's the difference from the reactants to the activated complex for the first step. Do the same thing in the second step, which begins here, and its activation energy is there. There's EA2. EA3 is here, and EA4 would be here. Now this is reading the reaction from the left to the right, so that's considered the forward reaction. You could read it in reverse as well. We'll get to that later. So which step was the fastest? Well, it's a little close, but I'm going to say that step 3, if I drew my arrows better, step 3 is clearly smaller than step 2. Those were the two possible choices there that were smallest. So step 3, because it has the smallest activation energy, you might want to put a reason beside your answer. The slowest step has the largest activation energy. And so the largest one of those arrows that I've drawn, that would be step 4. I guess you could get a ruler and check, but I'm pretty sure step 4 is taller than step 1. The slow step, the biggest activation energy step, is the rate determining step of the mechanism. What number represents the transition state formed in the first step? Well, actually, that's a mistake, isn't there? I think there's some numbers that did not print on this worksheet. So there is no number for the transition state in the first step. So rather than do that, why don't we just label it, this is the transition state or the activated complex, which is the same thing for step 1, right? So there should have been numbers at the top of each hill, I suppose, to answer that properly. So this would be the whatever's formed at the highest energy point in the first step, that's the transition state. Which numbers represent intermediates? Well, the intermediates are the products of the one step that become reactants in a later step. So in this mechanism, number 2, that would be whatever's formed at that point was the product of step 1. It's on the other side of the hill for step 1. But it's at the beginning of the hill for step 2, so those are intermediates. Number 3 as well is the product of step 2, but it's the start of step 3, so that would also be intermediate, and step 4 likewise. So steps numbers 2, 3, and 4. Is the first step endo or exothermic? Well, to figure that out, you look not at the activation energies, but you look at the difference from the reactants, where we began step 1, to the products of step 1. That difference is delta H for step 1, the heat of reaction or the enthalpy change for step 1. Because the end of step 1 is higher energy than the starting point of step 1, energy was absorbed. So that means it was an endothermic reaction. The delta H for step 1 is positive. So that would have been an endothermic reaction. The best way to say it is because the products of step 1 are higher energy than the reactants, or because delta H1 has a positive value. What does the number 1 represent in this diagram? Well, number 1 would be the reactants. Draw an arrow showing the activation energy of the last step. Well, I did that earlier. Let me do it again here. So from the activated complex or the transition state to the starting point of that step, that would be the activation energy for step 4, EA number 4. And the heat of reaction, the delta H for the last step, well, the last step began here and it finished at this energy level, so the difference there is delta H for step 4. And notice in step 4, the products are lower energy than the reactants, so step 4 would have been exothermic. It would have a negative delta H value. I'm going to leave you to figure out number 6 on your own. You're going to have to answer some true and false questions, as well as figure out what this missing step is. Start by figuring out the missing step. You do know the overall reaction, so think about what must have canceled out to get the overall reaction, and then fill in the missing step. Once you've done that, answer the questions on the side, true or false. We talked about this earlier, the molecularity of the different steps. Unimolecular, bimolecular, and termolecular are the 3 different molecularities that you will encounter. A single-step process, these are all single-step processes, are referred to as elementary processes. So these are the three different kinds of elementary reactions: unimolecular, bimolecular, and intermolecular. All right, so I'm going to leave this for you to complete. I think the rest of this assignment is pretty straightforward if you understand what we've done so far. So finish this assignment and I'll post my answer key on Google Classroom for you to double check.